Hello AP Chemers, this is the last lesson of the last chapter of AP Chemistry. We are talking about electrochemistry, and we have been seeing these boxes that keep saying we have electrochemical cells and electrolytic cells, and they are the exact opposites. So far we've been talking about electrochemical cells, which are batteries, and these are spontaneous reactions that produce electricity. So because they are spontaneous, your delta G is negative. Delta G is negative, and your cell potential is positive. So now we're going to look at electrolytic cells, which again are the exact opposite. And so these are non-spontaneous reactions. And so because they're non-spontaneous reactions, they won't occur on their own. We need electricity to drive a non-spontaneous reaction. So some outside force to drive these non-spontaneous reactions. Because they are non-spontaneous, their delta G's are positive and their cell potentials are negative. And again, they're kind of completely the opposite. So electrolytic cells, there's two different types of electrolytic cells. First, we have electroplating cells. That's when you want to plate something. So for example, if you have a coin and you want to put a thin layer of metal, of a different metal on the outside, you're plating it. So that's electroplating. So you use electricity to plate it, to put a thin layer of another metal on the outside. We have electroplating, and then we also have electrolysis. Electrolysis, lysis means to cut, and so we are going to use electricity to break down a compound. So we're going to start with electroplating. And again, because these are non-spontaneous reaction, we need an outside electricity source to drive the reaction, to force the reaction to go, because naturally it would not occur on its own. So this is what we use for the symbol for battery. And so this is your battery, because you need that electrical source to drive the chemical reaction. Like I said, everything is flipped. And so remember, we used to put the anode here and the cathode here for electrochemical cells. We're going to switch them. So the anode is going to be here, and the cathode is going to be here. And also, their polarities are switched. The anode now is positive and the cathode is negative. Remember, for College Board purposes, you do not need to know which one is positive and which one's negative. This is just for your notes for college. But now the anode is positive and the cathode is negative. The only thing that's the same about electrochemical and electrolytic cells is electrons always flow from anode to cathode. That's the only thing that's the same. So let's say I want to plate a coin. So I'm going to put the coin right here. This is my coin. And I'm going to put whatever I want to plate it with. So let's say I want to plate it with copper. So I'll put a chunk of copper here. This is my coin that I want to plate. Okay. I need a solution, and I'm going to, this is copper here. I'm going to put some copper solution here, so maybe copper nitrate. And what's going to happen at the anode, since this is oxidation, is that my copper will get oxidized. And so let's write the reaction for copper being oxidized. So copper would go from neutral copper to copper 2+, and it would lose 2 electrons. And so what's happening here is at the anode, my piece of copper, which is right here, is oxidizing, which means it's going to lose electrons and turn into copper 2+. The copper 2+ is going to go into the solution, and your electrons are going to go through the wire. So the electrons are going to flow this way. Okay, let's look at the cathode reaction. So the cathode is where reduction occurs. That is always true. Anode oxidation, cathode reduction. That's the same for electrochemical, electrolytic. Everything else is switched. So at the cathode, there's reduction, and so I'm going to take my copper 2+ ions, and I'm going to reduce them. So I'm going to take Cu2+, and I'm going to turn them into neutral copper. In order to reduce them, I need to gain electrons. And so what's going to happen here is that the copper 2+ ions are going to meet up with the electrons, and they're going to reduce to neutral copper. Where is the copper going to go? It's going to deposit on my coin. And so as time goes by, I'm going to keep plating that coin with copper. So as time goes by, this piece of copper is going to get smaller and smaller and smaller because it's undergoing oxidation, turning into copper 2+ and electrons. And as time goes by, this coin is going to get a thicker and thicker and thicker layer of copper on it. And so here we are forcing the electrons to go from the positive to the negative. Notice that? And that's not something that the electrons want to do, right? Electrons are negatively charged, and so they want to go from negative to positive, not the other way around. We're forcing them to go from positive towards the negative. And so in order to do that, you got to force those electrons, you got to push them with that outside battery. And so that's why we need a battery, because this would not normally be spontaneous. Electrons do not want to go that way. So electrons are pulled from the positive electrode, which is the anode in this case, and pushed towards the negative electrode, which is the cathode. Okay, again, you do not need to remember which one's positive, which one's negative. This is just for you to understand why this is not spontaneous. So let's look at this right here. We want to construct an electroplating cell with zinc and as the cathode and copper as the anode. So once we see electroplating, we think, oh, this is an electrolytic cell. Everything is switched. This is not spontaneous. We need a battery source for it. So to draw this, we are going to have our beaker, and we're going to definitely need our battery source. So short line, long line, short line, long line. I'm going to put 2 wires, and we are going to put the 2 pieces of metal right here. Remember, we switched everything, and so this is my anode, this is my cathode. You do need to label those. You do not need to label which one's positive, which one's negative. So it's telling us zinc is at the cathode, so this is my zinc, and copper is at the anode, this is my copper. And so let's look at what is happening here. They don't ask for the reactions, but since these are our notes, we want to show what's going on. So copper is being oxidized. So copper is going to Cu2+ and 2 electrons. I know that copper is oxidized because it's the anode, and anode is where oxidation occurs, cathode is where reduction occurs. So my copper is turning into Cu2+ and 2 electrons. Let's look up the cell potential here. So because this is oxidation, we've flipped the reaction. So when we look at our reduction potentials, our tables, because we flipped the reaction to make it oxidation, we're going to flip the potential as well. So the reduction of copper is normally positive 0.76 volts. The oxidation of copper would be negative 0.76 volts. Okay, let's look at the reduction at the cathode. Zinc is being reduced. And so if I'm reducing zinc, that means I'm going from the 2+ to the neutral. And to do that, I need to gain some electrons. My cell potential, or sorry, my reduction potential here. This is reduction, so we read it as is from the table. And on the table, the reduction for zinc is negative 0.34 volts. So it remains negative 0.34 volts. The overall reaction is copper reacting with zinc 2 plus to form copper 2 plus zinc. And my cell potential is going to be negative 1.10 volts. So what's happening here is that the copper is being oxidized. It's turning into copper 2 plus, which is going into the solution. This is a solution here. And I'm losing some electrons, and the electrons are traveling through the wire. This way. At the cathode, I'm taking zinc 2 plus. Well, where's my zinc 2 plus? Where is it coming from? Well, that must mean that my solution that I'm putting these electrodes in has to be a zinc salt solution. There's the zinc 2 plus. Put zinc nitrate here. So to figure out what solution it is, you need to figure out what your reactants are. What's being reduced is the one that you need the solution for here. So we're going to have zinc in the solution, zinc ions in the solution, so that we have our reactant here. So the zinc ions are going to meet up with the electrons, and they're going to form neutral zinc. So as time goes by, the piece of copper that's at the anode is going to get used up because it's turning into copper 2 plus, which is going into the solution, and electrons, which are going through the wire. And as time goes by, that zinc is going to get larger and larger and larger. So this is going to get more and more plated, or more and more deposited there. Let's look at our voltage here. So our cell potential, we said, was negative 1.10 volts. That matches up because this is a non-spontaneous reaction. We're forcing the electrons to go from positive to negative, which is not good. That's why we need a battery to force it to go that way. And so our voltage is negative. What that means is that I need to supply this with at least 1.10 volts. So this power source needs to have more than 1.10 volts to get this reaction to be forced to happen. So I need, based on this number, I need to supply more than 1.10 volts to get this reaction to occur, because it is non-spontaneous, and so I need my outside power source. Okay, so these are plating cells. Let's look at electrolysis, which again means breaking down. So we're going to take a compound and break it down into its elements. And we use electricity for that. So process of separating compound into its elements using electricity. Okay, there are actually two types of electrolysis reactions. We can melt our ionic substance. Remember, solids, it's really hard to get them to react, right? So we either melt them so that we're able to dissociate the ions, break that crystal and dissociate the ions, or we dissolve them in water in aqueous solutions. So melt or dissolve, either way, your ions can dissociate, and so they can undergo a reaction. So we're going to start with the molten one. So we're going to do molten CuCl2. So if I were to take copper chloride, copper 2 chloride, and melt it, and then I would connect it to electricity. So here's what I would do. I would get some sort of vessel. I need a battery source. And remember, the anode is here, the cathode is here. This is where oxidation occurs. This is where reduction occurs. I need my 2 wires here. And this is actually not a solution. It is a molten CuCl2. What is CuCl2 made up of? Well, it's made up of Cu2 pluses and Cl minuses, right? But this is not aqueous. This is just molten. Okay? So, what is going to happen here? Well, my reactants, what I have in here, is CuCl2, so Cu2 pluses and Cl minuses. So, in these two reactions, in the cathode and the anode reaction, this is reduction, this is oxidation. One of the reactants is going to be Cu2 plus, the other reactant is going to be Cl minus. Well, which one's which? Well, copper 2 plus. If it reacts and turns into copper, neutral copper, Cu2 plus to neutral copper, would that be oxidation or reduction? That would be reduction, right? Going from +2 to neutral. And so that's my reduction equation. That's what's at the cathode. Cu2 plus going to Cu. In order to do that, I need 2 electrons here. Okay? The other one must be the oxidation, but let's check. If chloride, Cl minus, goes to chlorine, neutral chlorine, well, -1 to 0, that would be going up in the oxidation state, which means you're oxidizing it, right? So Cl minus going to Cl2. So to balance that, you need a 2 here, and then 2 electrons. That's my reduction equation. So to figure out what your equations are, look at what ions are making this up, and you're going to go to the neutral elements. So Cu2 plus is going to go to neutral Cu, Cl minus is going to go to neutral chlorine, which is diatomic here. So let's look at what's happening in my cell here. So this is the anode, and so there's my chloride turning into chlorine gas, Cl2. And so my chloride ions that are in the molten CuCl2 here are turning into chlorine gas. And so at the anode, where that wire is, I'm going to see some bubbles. And this is Cl2 gas that is bubbling. Okay? So that's what's happening at the anode. The Cl minuses are turning into chlorine gas and giving off electrons, and the electrons are going to travel through the wire. Okay, what's happening at the cathode? Well, at the cathode, the Cu2 plus from the molten CuCl2 is going to meet up with the electrons, and it's going to produce neutral copper. And neutral copper is a solid, so it's going to plate on this wire right here. So my 2 wires, I would see some solid copper on there, on one of them, and on the other one I'd see bubbles, and it would smell like chlorine. Now, how much metal here, how much copper gets plated, whether it's here or whether it's in an electroplating cell, depends on 2 things. It depends on the voltage of your cell here. It also depends on the time. How long do I leave it? Obviously, the longer I leave it, the more plating will occur. So in an electrolytic cell, current is important, what current I'm providing, and it's important to remember that 1 ampere is equal to a coulomb of electrons per second. Let's write that down here. 1 ampere is equivalent to 1 coulomb per second. So let's say I have a current of 1.50 amperes, that means 1.50 coulombs per second, flows through an electrolysis cell of molten or melted copper to chloride for 15 minutes. How many grams of pure copper are plated out? How do I do this? Well, start with one of the numbers they give you, either with the 1.50 amperes or with the 15 minutes, and use your units to try to get to grams eventually. So I'm going to start with 15 minutes. And my other number is coulombs per second, so let me change this to seconds. So minutes here, seconds here. 1 minute is 60 seconds. Okay, I'm at seconds. Well, let's get rid of seconds. I don't want seconds, so let's multiply it by the 1.50 coulombs per second. Okay, I'm at coulombs now. What do I do? Well, remember that 1 Faraday is equal to 96,500 coulombs. Good. I'm going to cross out my coulombs. Well, what's a Faraday? Well, a Faraday is a mole of electrons, right? So let's put 1 Faraday is 1 mole of electrons. We're getting somewhere now. Got moles of electrons. But we wanted moles of what? We wanted moles of copper, right? So let's think about this. Let's look back at our reaction. For every 2 moles of electrons, I plate 1 mole of copper. So let's do that. For every 2 moles of electrons, I plate 1 mole of copper. There we go, we're at moles of copper. Now, last bit, go from moles of copper, 2 grams of copper. 1 mole is what, 63.5, is that right? Yep. Moles of copper cancel, we get grams. Isn't that cool? If you started out with the coulomb per second with the amperes, you can still get to the same answer. You know, just keep crossing out your unit, try to get to somewhere. But the key here is this right here, that 96,500 coulombs is a Faraday, and a Faraday is a mole of electrons. And that's where you're going to go from, you know, coulombs to eventually moles of the substance. When you multiply this through, you get 0.44 grams. Let's try another one. It says, in a silver plating cell, if a maximum current of 1.5 amperes, and again, as soon as I see amperes, I write coulombs per second. So this is coulombs per second. Is supplied, how long will it take to produce 1.0 grams of pure silver? So this is the opposite question. In the previous one that we just did, we were given the time and the current, and we were asked for the grams. Now we're given the grams, and we're asked for and the current, and we're asked for the time. So let's start with my 1 gram. Again, if you start with the 1.50 coulombs per second, that would work as well. So I'm going to start with grams of silver. I'm going to go to moles of silver. It's the link between anything. It's always moles, right? 1 mole of silver is 107.9 grams. Okay, got 2 moles of silver. Now let's go to moles of electrons. Well, how am I going to go from moles of silver to moles of electrons? Well, if we are depositing silver, that means we are going from silver ion, which is +1. And so I'd need to gain an electron, just 1 electron to get to the silver. So 1 to 1. Okay? Remember that 1 mole of electrons is equivalent to 1 Faraday. And that 1 Faraday is equal to 96,500 coulombs. And we know that we have a current of 1.5 coulombs per second. Isn't that clever? I love when my units cancel and I get what I want. And so I actually converted it to minutes. I don't know why. You don't need to convert it to minutes, but my answer here is in minutes. 1 minute is 60 seconds. I got 9.9 minutes. It is fine if you leave it at seconds, of course. It doesn't specify what units of time you want. Okay, so we said electrolytic cells can be electroplating or electrolysis. Electrolysis is when you take your compound and turn it into its elements using electricity. And we said that a solid wouldn't work. You have to dissociate the ion somehow, so you can either melt it or you can dissolve it in water. So let's look at dissolving it in water. So here I'm going to have my vessel or beaker where my aqueous solution is. And so here I have water, and I have Na pluses and Br minuses. If it's electrolytic, then I need a battery. I need wires. This is my anode. This is my cathode. This is where reduction occurs. This is where oxidation occurs. Okay, so we have sodium ions and bromide ions. So Na pluses and Br minuses. Let's look at Na pluses. Well, when this reacts, we're going to decompose it into its elements, right? And so sodium ion would become sodium, the metal sodium. And so Na plus going to Na, that's a reduction. Going from +1 to 0, that's a reduction. So I'll write it here. Na plus yields sodium, and I'd need an electron to do that. Let's look up the cell potential, or the reduction potential for this. The reduction potential for sodium is -2.71 volts from our table. Okay, let's look at the oxidation. So it must be the Br minus, but let's think about it. Br minus, when it turns into bromine, that's Br2, neutral Br2. And so I'm going from -1 to neutral, 0. And so that's an oxidation. So Br minus going to Br2. Let's balance it. We need a 2 here. And we need 2 electrons. My potential, remember that this is oxidation, so I need to flip my potential. And so looking at the reduction table, my potential is for reduction is positive 1.08 volts. This is oxidation, so we flip it, so it's negative 1.08 volts. Okay, now this is not just Na pluses and Br minuses, there's also water in there. So why not water undergo oxidation or reduction? Well, it can. So I want you to look at your table of reduction potentials and see if you can find the reduction and the oxidation of water. So pause the video and see if you can find them. So in one of them, you're going to find the reduction. So you're going to see water and in the reactants, and you're going to gain electrons and then produce something. The other one's going to be the oxidation, so oxidation would be flipped. So the water would actually be in your products, because when we flip it, then it would be in the reactants. So pause the video for a second and try to find them. Okay, let's start with the one where your water is being reduced. If you look at where it says basic solution here, you'll see water plus some electrons, and you yield this right here, and the potential is -0.8277 volts. This is your reduction for water. That's the equation you're looking for. Now let's look at the oxidation one. So the oxidation one, because these are all reduction equations, the oxidation one, the water is going to be on the product side, and the electrons are going to be in the reactant side. So let's see if we can find that one. You go to this page right here where it says acidic solutions, this one right here. So you have water, and if you're looking at the reverse reaction, because it's oxidation, so it's going to produce all these things plus electrons. And the cell potential, the reduction potential here is 1.229. So if we flip it, the oxidation potential will be -1.229 volts. So let's write those down in our notes, those two equations here. So let's start with the reduction one. The reduction one was 2H2O plus 2 electrons yields H2 plus 2OH minus. And the potential for that one was -0.8277 volts, I believe. And the oxidation one, so flip the reduction equation, you get 2H2O yields O2 plus 4H plus 4 electrons. The potential, since we flipped the equation, is also flipped, -1.229 volts. Okay, so why are we putting these in? Well, because water could also get oxidized or reduced. So what actually happens? Do both of them, all four things, occur? Well, it depends on your power supply. The one that's more likely to occur is the one that needs the least amount of voltage. And so comparing these two, in order for this to happen, I supply 2.71 volts. In order for this to happen, I only need to supply 0.8277 volts. So this one is more likely to occur. This one's going to occur faster, or first, I should say. If you are supplying enough voltage, then you can reduce this one and then start reducing that one. Both of them can happen, but this one is the one that's likely to happen because you need less voltage to get it to go. Comparing those two, this one needs you to supply 1.08 volts. This one needs you to supply 1.229 volts. And so this one needs less voltage for it to occur. And so this is the reaction that's going to occur. And so let's look at our cell here. At the anode, where the oxidation occurs, the bromide ions are going to turn into bromine. And so bromine will bubble here. Depends on like how warm it is. Bromine is a liquid at room temperature, but it easily vaporizes. So you might see bubbles of bromine gas, or you might see bromine liquid going in here. So it's going to turn into bromine, and then the electrons will flow through the wire. And at the cathode, the water is going to meet up with the electrons from the wire, and it's going to turn into H2 and OH minus. So you'll see bubbles here that are H2 bubbles, H2 gas, and you're also going to be producing OH minuses, which is basic. So your solution will actually turn basic as well. If this was happening, then you would see acid forming. So if you do just water by itself, so that this reaction occurs and this reaction occurs, that's actually pretty cool because you can see it with, you'll see bubbles, and you'll see that one is acidic and one is basic if you add an indicator in there. Okay, let's look at this last question here. It says, which reactions take place given the following? So it looks like, oh, one of them got cut off. Sorry, let me add one more. Z plus an electron yields Z. The potential for that one is negative 2.70 volts. Okay, so it looks like we have two oxidation and two reduction reactions. Let's see which one's more likely to occur. So Y and X, they are being oxidized. This one needs 0.94 volts of voltage to be supplied. This one needs 0.14 volts to be supplied, and so X is likely to be oxidized. Okay, let's look at the reduction ones. So we have W and Z. Those can be reduced. This one needs you to supply 1.70 volts. This one needs you to supply 2.70 volts. So the one that needs less voltage to push it to go is going to be the one that occurs. All right, have a great day, guys.